Hello everyone, welcome to my video on differentials. So differentials and linear approximation go hand in hand. They're very similar concepts. So let's take a look at the geometric interpretation of what's going on here. So we have originally the function f of x in green, and then we have the equation of a tangent line in red over here passing through this point here. So this point, let's call it x. And if we shift away from x, we use this idea when we're talking about the equation of a tangent line. We shift it over by h, but instead of calling it h, we're just going to call it now delta x. So let's change or move away from x by delta x. Let's go over here. So if we shift over by delta x, this value here would be x plus delta x. Okay. And now let's look at what happens to our functions. We'll hit this point here and we'll hit this point here. Let's call this point here S as the starting point, and let's call this point here F, and the point on top, let's call it T for tangent. So notice that S and T are on the tangent line and S and F are on the function f of x, the original function. So let's focus on the original function. What's the difference between S and F on the x-axis? Well, the difference between S and F on the x-axis, we're asking for this distance here, from the point S to the point F, is just x plus delta x minus x. So the x's cancel, giving us delta x. This distance here is delta x, the change in x of the actual function, the original function in green. And now what's the change between S and F in terms of y? Well, that function, sorry, not that function, that distance is from here to here. So the y value of here to the y value of s, giving us this is delta y, the change in y from the actual function. Okay, now let's look in terms of the tangent line, because again, we know the closer we are to this point, the difference between the function and the tangent line is very negligible. But the further we get away from this x value, or this point where the function hits the tangent line, the further we get away, the larger the difference between the tangent line and the original function. And this is the idea. So we're going to call the distance in the vertical distance y, we call it delta y, but using differentials. So we call it dy. So the difference in the y from point S and now point T on the tangent line is your dy. Okay, and the distance between the S and T in terms of x, we'll notice that it matches delta x. It's equivalent because the x of this value is the same as the x of this value. So that's your dx. So this is the geometric interpretation of differentials. So we have the definition. So let's write down our formula that we know. We know that f prime of x, using Leibniz notation, can be written as dy dx. Okay. And our formula for differentials is essentially just if dx on the bottom is not equal to 0, what you could do is multiply on both sides of this equation by dx. So if we multiply by dx, what we get is dx times f prime of x, and that's equal to dy. And that's the equation for differentials. dy equals dx times f prime of x. So we know that dy is equal to f prime of x times dx. From our geometric interpretation, we know that dx is equal to delta x. The only thing we're missing now is delta y. What's the equation for delta y? Well, delta y, the way you would find it is you would plug in x plus delta x into the function, and you would plug in x into the function, and then subtract those two answers. So delta y is essentially, you could think of it as y2 minus y1, or it's just f of x plus delta x minus f of x, which is similar to the numerator of our derivative definition, but instead of delta x, we were using h. So notice that this is an equation that we also have to use. Okay, let's take a look at a couple of examples and we'll apply these formulas. So in our first example over here, it says find the differential dy given the function y equals ln of square root of x squared plus 1. So let's go ahead and do that. So first of all, the differential dy, using our formula, it's dy equals f prime of x times dx. And we're essentially just taking the derivative of this. with respect to x. So taking the derivative, let's do this on the side. I'm going to call it y prime, but we know that f prime of x is equal to y prime. It's the same thing. So y prime, it's the derivative of ln. Another thing is I'm just going to rewrite this as ln open bracket x squared plus 1, all that to the 1/2. Okay. And a nice property, if you're solving this on your own and you decided to do this, you could drop the exponent of the 1/2 in the front just to make it easier. So we could actually, using log properties, is write it as a half ln of x squared plus 1. Okay. If you didn't see that, you still have to use chain rule, but this is a lot easier. It's still chain rule, but an easier version. So I'm going to take the derivative of this term. So since we have the 1/2 in the front, I'm just going to leave it in the front. And now we're going to take the derivative of the inside, giving us 1 over, the derivative of ln of x is 1 over x, so the derivative of ln of x squared plus 1 is 1 over x squared plus 1. We don't stop there, multiplied by the derivative of what's in the inside. Chain rule, don't forget chain rule. So the derivative of x squared plus 1 is 2x. Okay. So simplifying here, we get the 2's that cancel, and this is just x over x squared plus 1. So the differential, it can be expressed as f prime of x, which we just showed is x over x squared plus 1, and then we leave the dx here. Okay, so a very simple example, we're just applying the formula and essentially taking the derivative, and at the end we're just multiplying by dx. So in this next example, we're asked to find dy and delta y, and then we'll compare the difference between the two answers. They give us the function y equals 2 over x, they give us x equals 4, and they give us delta x equals 1. So let's go ahead and solve that. So we have to do both of them. So let's start off by finding, we'll start off with dy. So we know dy by our formula, it's f prime of x times dx. And f prime of x, well, the function that we're using is 2 over x, so we have to take the derivative of that guy. So let's go ahead and do that. F prime of x is equal to 2 over x prime. So you can use quotient rule. I want to avoid quotient rule, so I would bring the x up and you work with 2 times x to the negative 1 and then just apply power rule. Okay, so let's go ahead and do that. So this could be written as 2 times x to the negative 1. So we're bringing the x up and we're going to take the derivative of this guy. This gives us negative 2, so the 2 is a constant, we leave it in front. Not a constant, sorry, it's a coefficient. So it's a constant multiple, leaving it in the front. We're going to drop the negative 1, giving us negative 2, and then we're going to subtract 1 in the exponent, leaving us with negative 2 times x to the negative 2. So we could rewrite this as negative 2 over x squared. Using quotient rule, you should get the exact same answer. Okay, but we're not done. We have f prime of x, which is this guy, times delta x. What's our delta x in this case? Well, they tell us the difference between the x is 1. And we know from our rules that delta x is equal to dx. So dx is equal to 1. So dy equals negative 2 over x squared times 1. Okay, from our formula up here. But we know that x is equal to 4, so we could actually find a numerical value for dy using the fact that x is equal to 4. So this is negative 2 times 1, it just stays negative 2, 4 squared. So that's 16. This gives us negative 2 over 16, which is negative 1/8. So the value of dy is negative 1 over 8. Now let's go look at delta y. So the formula for delta y we said was f of x plus delta x minus f of x. So let's substitute our values into our function. So delta x equals, oh sorry, not delta x, delta y. We're looking for delta y. So delta y equals f times, f of x plus delta x minus f of x. So delta y equals f. We know what x is. X is 4. So 4 plus delta x is 1. So plus 1 minus f of x, which is 4. So to find delta y, all we're doing is f of 5 minus f of 4. This is equal to, So f, the function that we're using, is just 2 over x. So this is 2 over 5 minus 2 over 4. So we're subtracting fractions. We have to find the common denominator. So in this case, it's 20. So 4 times 2 is 8 minus 5 times 2 is 10 over 5 times 4 is 20, leaving us with negative 2 over 20, which is negative 1/10. So as you can see, the answers are very close to each other, but not exact. Okay, so this is the approximated value, this is the exact value. So I just want to add, negative 1 over 8 can be expressed as negative 0.125. And negative 1/10 could be expressed as negative 0.1. So these values are very close to each other. So they're not that off. My question to you is, what would happen if delta x was 2 instead of 1? And also, what would happen if delta x was equal to 1/2 instead of 1? So you should be able to answer what would happen to our values here. Would they get larger or closer to each other? So if delta x gets larger, then we would expect the difference between our answers to be larger. If delta x is smaller, let's say it's 1/2, then we would expect these values to get closer. So the closer delta x gets to 0, the better the approximation will be. So keep that in mind. So in this example here, we have an orange which has a radius of 4 centimeters. This is the orange without the peel. And we know that the thickness of the peel is 1 millimeter. Use differentials to estimate the volume of the peel. So there's two ways of doing this. We'll use differentials, and then we'll do it the other way where you don't have to use differentials. You just calculate the volume of the entire orange with the peel, then calculate the orange without the peel, the volume of the orange without the peel, and then you subtract your answers. That's the delta y method. Let's use differentials and compare our answers. So using differentials, we have our formula. Let's maybe draw the sketch first. We have our sphere, and then we have the peel. So this is the orange, and then this is the peel on the outside. We know that the radius is r, and we know that the thickness of the peel, I'm just going to write it here, is delta r. So this is the thickness of the peel. So if I were to just take the peel, its thickness is delta r. So we know that the radius, based off the information, is 4 centimeters. And we know that the thickness of the peel is 1 millimeter. So we have to be careful. We have to ensure that we convert and we use the same units. So 1 millimeter, that's our delta r. So you could either put everything in millimeters or you could put either everything in centimeters. Let's go to centimeters. So 1 millimeter is equal to 0.0121 centimeters. Okay, so you move the decimal, which is after the 1, twice to the left. And now let's use our differential equation. So we know that dy is equal to f prime of x times dx. Okay. But since we're using the radius, we're not using x, we're using the variable r. So f prime of r dr. dr is the same as the delta r, the change in the radius. So dr we have, let's write it down here, the change in the radius we have. What we don't have is f prime of r. But what are we taking the derivative of? What's the function that we're using? Well, if you're talking about the volume of the orange, you're using the volume of a sphere equation. Okay, so let's keep that in mind. We have v equals, the volume of a sphere is 4 pi r cubed over 3. And if you think of this as a function of r, instead of volume, we'll just write f of r. Okay, so we have to take the derivative of a sphere, of the volume of a sphere equation. So the derivative of this is actually very simple. It looks complicated. It looks like you have to use maybe product rule, quotient rule, but you don't. All you have to do is realize that 4 pi over 3, those are just constants, or I should say a coefficient. They're constant multiples. So all you really have to take the derivative of is r cubed. Okay, and we're deriving with respect to r. So this gives us 3r squared. Okay. Notice that the 3's cancel and we're left with 4 pi r squared. Notice that this formula should look familiar to you. It's the equation of the surface area of a sphere. So I mentioned a long time ago that the derivative of the volume is the surface area, not for all shapes, but it works out for spheres. So this is the equation that we're using here. So delta y is equal to f prime of r, which we got is 4 pi r squared, times dr. Okay. the radius we have, the change in the radius we have, so we just plug everything in. So 4 times pi times r, which is 4 squared, times the change in r, which is 0.01. Okay, let me use a calculator. So what we get is 4 cubed times pi times 0.01. So I get 2.01 about centimeters cubed. Okay, so the change in the volume is about 2 centimeters cubed, or not the change in the volume. Think of it as the volume of just the peel without the orange in the inside would be 2.01 centimeters cubed. Now let's go ahead and do this. So this is our final answer using the differentials. Let's go ahead and compare our answer using the delta y equation. So using the delta y equation, we have delta y equals f of x plus delta x minus f of x. Okay. But instead of using x, we're using the variable r. So we're going to switch this with r's. We have a radius, the change in the radius, and the radius. Okay, so r plus delta r we know is 4 plus 0.01, so it's f of 4.01 minus f of just the radius, which is 4. But again, what's our function? Well, the function is, we're trying to find the difference in the volume. So the function that we're using is our original volume equation that we just used before. So the volume equals 4 pi r cubed over 3, so the volume of a sphere, and this is our function in terms of r. Okay. So we're just going to plug these two values into this function here. So what we get is 4 pi 4.01 cubed over 3 minus 4 pi. Notice that we didn't take the derivative this time, we're just plugging into the original equation. 4 cubed over 3. Okay, so let's go ahead and solve that. This gives us, I'm just going to factor out the 4 pi over 3, leaving us with 4.01 cubed minus 4 cubed. Okay, let me use a calculator. So 4.01 cubed minus 4 cubed, we'll do that at the same time, and then times 4 times pi divided by 3. Let me do everything in one shot. It gives me about 2.01565, so on and so forth, centimeters cubed. So this is the actual volume of the peel of the orange, 2.01565, whereas when we use the differential, our estimation was about 2.01, and that's a very close and good estimate. Okay. Notice that here delta r was just 0.01 centimeter, which is really close. So the closer this is to 0, the more accurate our answer is going to be. And as you can see, compared to the other example, this is a way better comparison and estimation. Okay. So I hope that helped, and I'll see you in the next video.